Ladies and gentlemen, welcome to class. Today we will introduce attention and the transformer for natural language processing. What is attention? Attention is a mechanism that exists in our brains. To prove this, here is an attention test. The test asks you to find where is the four-leaf clover. There are a lot of three-leaf clover. Where is the four-leaf clover? This test comes from the concentration test. There are many similar tests. Those tests show us that our brain can automatically focus on or pay attention to the important information amidst a lot of noise. We receive tremendous amount of information every day. The attention mechanism can help us understand the information. There are two examples. One is visual attention and the other one is textual attention. Here's a picture of a dog in human clothes. The visual attention of our brain can focus on the features of the head and understand those are dog's features. So we know that this is a picture of a dog, not a human. For text, here's a sentence which says she is eating a green apple. To understand the meaning of this sentence, we will first focus on the verb eating, and then we find the relationship. There's a high attention between eating and apple. So focus on eating and the apple. We can understand that this sentence means that she is eating a green apple. However, the green is not important in this case because it's just used to describe the color of the apple. So the eating and the green has low attention. How can we implement the attention mechanism in neural networks? In practice, we simply learn a vector of importance weights. We use the weight vectors to assign importance of input data. There are different types of attention. First, we have implicit attention and explicit attention. In fact, we have implicit attention in convolutional neural networks. Max pooling can be considered as a type of implicit attention. Remember, the max pooling is to select the region that has highest feature response, the largest feature value. So it's actually select one of the most important region. So it's a type of implicit attention. Another different types of attention is hard attention and soft attention. Soft attention is described by continuous variables, while hard attention is described by discrete variables. Next, we have additive attention and multiplicative attention. Suppose we have two inputs. One is the current state, current hidden state, and the other is the context, which are the previous states. And we use the previous context with current input to calculate the attention. Additive attention use one neural network, one hidden layer to calculate the output, while multiplication just multiply the attention weight with the current hidden state and the context. Attention has been widely used in natural language processing, especially language translation. We use the sequence-to-sequence model for language translation. Sequence-to-sequence means that we want to translate one language sequence into another language sequence. So here we translate French into English. The RNN encoder encodes the input French into embedding vectors and then sent to the decoder. The decoder will decode the input embedding vector into the target sentence. So remember, there's only one neuron in RNN there. So this is the expansion of RNN on the timeline. So if we have 4 words in the input sentence, we will first input the word embedding vector into the RNN there, and then input next word with the output to calculate the new output. Okay, this is RNN, and we have 2 RNN, encoder RNN and decoder RNN in the sequence-to-sequence model. In order to train the sequence-to-sequence language translation model, for the encoder, we just input the input language. Suppose here is English, but for training the decoder, we also need to input the correct translation. Here's the French. So the input is the correct answer. So when we receive the embedding vector, we will first pass the star, and then the decoder may output this. And then we will input the correct answer into the decoder, so we can train the correct decoder. But for the inference phase, we just use the output of the decoder as the input for next stage of the decoder RNN. Now, this is straightforward. During training phase, we have the answer, right? So we use the answer as the input, as the output of previous stage. But in the inference phase, we don't have the correct answer, so we just use, as typical RNN, use the output of previous stage as the input. RNN can consider the order of words, which is good, but not good enough. To understand the words better, we need to know the context. The context are the neighbor words of the target word, the words before and after the target. Suppose the target is the date, then the context is the words before and after the target word, date. Why we need to know the context? Because we have harmonious. Words usually have multiple meanings, and the meanings depends on the context. Here are 2 examples from the harmonious. The words with multiple meanings. First example is date. There are 3 sentences. The first is her favorite fruit to eat is a date. Here date is a fruit. Okay. And the second example, the second sentence says that the John took Mary out on a date. So the date means a romantic appointment. The third sentence is what's your date of birth? So this is the specific day of your birthday. The second example is fall. The first sentence says, I love cool, crispy fall weather. So this is about season. The second sentence says that don't fall on your way to the gym. Also, it reminds you that don't fall down. From this example, we know that we need to understand the context to have better explaining, better understanding of the input sentence, of input words. The attention mechanism can help us understand the context. Here is an example of additive attention in RNN. Suppose we use the bidirectional RNN as encoder. It's very common because we can have two sentences have same meanings in different orders. Okay, and we can add an attention layer. The attention layer will give the weight to different output, different hidden state in the RNN. So we need to record the output, no, record the hidden state at different time, and we assign different attention weight to them. Then we use one hidden layer to calculate the weighted sum and go through an activation function. Then we pass the output to our decoder. This is additive attention. The additive attention layer helps us to consider the context in the sentence and also help us to pay attention or to have higher attention weight for important input. In 2017, Google Brain and the University of Toronto have published a breakthrough paper. The title is "Attention is All You Need." The title says everything. The researchers propose to use attention module in their neural networks to replace recurrent neural networks, and they show that their new model, they call it transformer, can outperform other state-of-the-art models on multiple NLP benchmarks. And this paper goes beyond natural language processing, and the researchers start to use attention module in also vision, computer vision, and replace convolutional neural networks. It has affected all fields of deep learning now. The authors call their attention-based neural networks transformer. This is the picture of transformer from the original paper. The author proposed a multi-head attention and used the attention in encoders. They used the module to calculate attention of the input sequence and call it self-attention. So they use the self-attention in encoders and the mask self-attention in decoders. Because the decoder can only see the inputs before the current inputs, it can only see the previous input. So they use a masked self-attention, and also they add the encoder-decoder attention. Let's look at this picture. This part is one encoder, and this is one decoder. You can have multiple encoders. You can stack multiple encoders. And each encoder has one multi-head attention and one feed-forward network. They add the layer normalization at the output of the two networks. So one encoder is one multi-head attention with one feed-forward network, and also it has a residual connection. For the decoder, it has a masked multi-head attention for the input, and it has a encoder-decoder attention. So from this picture, we can see that there's no RNN or CNN in transformer. Transformer use a lot of attention, and the experiment results show that the performance can be best among many NLP benchmark. Finally, before input the data, the author adds the positional encoding. The positional encoding is to save the input order because attention does not consider the word order. It does not consider the order of words, so we need to add positional encoding information to the input vector to preserve the original order of the words. Here is the attention module in transformer. The module has 3 inputs: query, key, and the value. Here's the formula. We can look at this picture. Try to visualize the formula. First, we use query and the key to calculate the attention score, to calculate how important of each part of the data. And then we do normalization using the dimension of the query and key vector. We use the square root of the dimension. And then we can pass the data through a mask. Remember the masked self-attention in decoder. So we can pass through a mask to mask out some data. Then the output vector is sent to softmax. Softmax will normalize a probability distribution. Finally, the output vector will be multiplied by the input value. So we use the score to calculate the importance of the data in the input value vector. So this is the attention module used in transformer. Google provides a notebook to visualize attention. It's called Tensor to Tensor notebook. Here's the link. The example try to translate English into German. The input is the animal didn't cross the street because it was too tired. And this is the German version of the input. So from this picture, we can see that the input is here. The animal didn't cross the street because it was too tired. And first is have multiple layers because we can stack multiple encoder and decoder. And you can select to show all attention or just input to input, the self attention in encoder or the self attention in decoder. We select all, so we can see that the because is connect. The attention is calculated between the inputs here. The English, the animal didn't cross the street because it was tired, and the output is here. So if you select all, it will show the attention scores of all the input and output. We have input, output, encoder, decoder, attention. And then the color is the layers. We have it's the head. We have multi-head attention, right? So each attention we will have multiple attention score. It's like the channel in an image, right? So in this case, we have how many head? We have 8 head, and the color shows that if the color is more saturated, then this connection, this attention is more important. Let's look at a self-attention example. We select the input to input attention, which is the self-attention in the encoder and the layer 5. Then we select it to see which words in the input sentence is more relevant to it. So the words that has highest attention scores are the animal. So this is correct because the it means the animal. The animal didn't cross the street because it. So from this example, we can see the attention has successfully learned the right attention score with the words in the input sentence. This is self-attention. It also has some relevance with the street because the animal didn't cross the street. Go to play the notebook by yourself and you will understand attention mechanism better. Now let's look at more details about self-attention. Let's try to calculate a simple self-attention. Suppose we have an input sequence. The train left the station on time. We have 7 words. And we want to calculate the attention scores of station. We want to know the relationship between station and other words in the sequence. We can use the attention score matrix. Suppose we have learned the attention score matrix. This matrix shows the attention scores between words in the input sequence. So this is self-attention in the encoder, although it's not totally the same as the transformer attention module, but it shows the mechanism of attention. Then we can select the vector station attention, the attention vector for station. Right, so here is the scores for the station. Then we multiply the station scores with the input vector. Then we do the scaling and multiplication and pass the data through softmax function to normalize the probability distribution. Finally, we calculate the weighted token vectors. For each token, we calculate the weighted weighted token vectors. Then we sum all the vectors to calculate the new context-aware vector. This is how we calculate the self-attention of the input sequence. Let's look at the self-attention pseudocode. So to calculate self-attention, first we input the input sequence. Then we iterate through the input sequence. We iterate over each token in the input sequence. And the current token is called pivot vector. And then we calculate the dot product of the pivot vector and the other vector, other token vector, attention vector in the attention matrix. So basically, attention score is calculated by dot product. We compute the dot product attention scores between the token and every other token in the attention matrix. Then we calculate square root of the score. We scale and normalize the value. We square root of the dimension of the input, and then we calculate or paste the data through the softmax. So finally, we take the sum of all tokens weighted by attention scores. Here we use the attention scores to calculate the weighted sum of the input vector, and then the sum all the tokens, weighted tokens together. And this is our new output, new context-aware output. So this is the pseudocode of self-attention. The self-attention we have done in previous slides can be summarized in this formula. So we first calculate the pairwise scores between the words in the input sequence. So we calculate the attention score of each input word with other words, the context in the input sequence. And then we multiply the attention score, the pairwise attention scores with the original input. This is self-attention. But remember, in transformer, the attention module is query, keys, and the values. So where are the query and the keys and the values? So actually, the input, the pivot input, can be viewed as query. The current input word is query, and the other inputs in the input sequence, the other words, the context can be viewed as keys. So the query and the keys are used to calculate the attention scores. But in self-attention, both query and keys are inputs. And then the attention scores can be used to calculate what is sum of the values. So here are the query keys and values. And remember the original formula in attention is all you need paper. So they just calculate all the calculations we have done can be done in matrix multiplication. So it's just the query matrix multiplied by the key matrix and do normalization. And pass through softmax to normalize the probability distribution binary multiplied by the value matrix. So the total process is very efficient because all the calculation can be done in matrix multiplication. So this is the attention module used in the paper. Query keys and values. And the self-attention just use inputs for query keys and values. So if all the three inputs are input sequence, in other words, if you use input sequence for query keys and values, then this is called self-attention. The query keys and the values idea comes from information retrieval, the search engine. So for search engine like Google, we first pass the query. The query, for example, could be a sentence, dogs on the beach. Then we want to use this to search relevant images. And the images, here the values are images, will be indexed by the content. So we have keys for each values, the keys for the images. The keys describe the items in the image. For example, in this picture, we have beach and a tree and a boat. So the query makes the first key. So the match score, the attention score may be 0.5. The next value, the next image has beach and the dog and the tree. So the attention score is higher than first one, or it may be 1. And finally, there's an image of a dog, but no beach, so the attention score may be 0.5. So the second image has higher match score because it's matched two items, two words in the query sentence, query sequence. Okay, this is how the attention module try to do. It try to learn the attention scores for the query and the keys of attention matrix, and then it can use query keys and value to calculate attention. The multi-head attention is to learn multiple attention modules at the same time. Because the input sentence are usually very complicated in practice, it may be very long, and we need to learn different attentions in the same sentence. So it's useful to learn multiple attention modules. Each module will learn different attentions for the input. So it's actually multiple the query key value attention module, H modules. So multi-head is just use multiple attention modules and concatenate the outputs. It's like the dead-wise separable convolution in convolution neural networks. Let's look at the transformer encoder architecture again. So first it has the multi-head attention module, which is here. And then it has a feed-forward network, which includes multiple dense layers. And then it includes the residual connection. So modern networks usually include a residual connection, which can reduce the gradient vanishing problem. And then it uses the layer normalization, we know bench normalization, right? It's similar to bench normalization, but it's just normalize the whole output layer also. So the overall transformer encoder include one multi-head attention module and the residual connection, layer normalization, feed-forward network, residual connection again, and then layer normalization output. This is one encoder, and the transformer has multiple encoders. We can implement the transformer encoder using the multi-head attention module in Keras. First, we define the transformer encoder, inherit from layers dot layer in Keras, and then we define the initial embedded vector dimension and the dense layer dimension and the number of heads. So this is the size of input token vectors embedded vector dimension and the size of the inner dense layer. Then we create a multi-head attention layer and save it as attention. Also the feed-forward network, two dense layers. Okay, the dense project layer. Once the function once the class is called by other class, we try to create the module. First, we need to expand the mask. The mask will be generated by embedding layers. That will be 2D, but the attention layer expects to be 3D or 4D, so we need to expand the rank of the mask first. Then we set the output of the attention layer. We pass two inputs into the attention layer because it's self-attention, and then here's the attention output. Then we pass the output plus the original input or the residual connection to normalization, layer normalization, and got a new projection input, the input for projection layer. Then we pass the input to the dense projection layer, the feed-forward networks, and have a new projection output. Then here's the residual connection again, and finally we add one more layer normalization there. So that's it. That's the basic architecture of transformer encoder. We will have one more function which is called getConfig. We can read the definition of embedding dimension and the number of heads or dense layer dimension from file. We can get the config. We can pass the config and save the config to disk. In transformer, we use layer normalization. We have used bench normalization for images. The difference between layer normalization and the bench normalization is that the layer normalization compute the mean and variance along the lattice axis. The input shape is bench size, sequence, length, and the embedding dimension. So the layer normalization calculates the mean and the variance along the embedding dimension. For the bench normalization, is calculate a pool data over the bench axis, axis 0, which creates interactions between samples in a bench. So that's the difference between layer normalization and the bench normalization. We can use the transformer encoder to extract features. So we can use only the encoder. We don't need the decoder part to classify text. So the encoder encode the text data, right, like the feature extraction in images. Okay, so we want to use the transformer encoder built before. First, we defined the Keras input and then the embedding layer, which embed the one hot word vectors into embedding vectors, and then the transformer encoder, which accept the embedding dimension and the dense layer dimension, which is 256 and 32 here, and we have two heads. So we pass the embedding output to the transformer encoder, then finally we do global max pooling 1D, then drop out. So this is our transformer encoder. Because we want to classify the IMDB movie review. Remember, our goal is to classify a review into either positive or negative. So it's a binary classification. So we add one activation layer or sigmoid layer for the binary classification. Finally, we use model to connect inputs to outputs, then compile it. Use binary cross entropy loss and accuracy as metrics. Then this is how to use transformer encoder to classify IMDb review. Let's compare different types of NLP models. In previous class, we have learned to use the multi-hard embedding vectors to classify IMDb review. Also, it's called the bag of unigrams if we only consider single word, or bigram if we consider two words, one and two words together. The bag of unigrams does not know the order of words. It's just the statistics of the words in a review. And it's not context aware. It's not context aware because it does not consider the crossword interactions. The bag of bigrams has limited word order. It's considered two words, so limited word orders, still not context aware. The RNN consider the order of words, right? Because it's consider the whole input sequence, but it's not context aware. Self-attention consider the context of is calculate the attention score for the input sequence, so it's context aware. But it does not consider the order of word. Calculate the attention scores does not consider the word order. So to solve this problem, transformer add positional encoding to consider the word order. Also, transformer consider both the word order and the context. Let's look at the positional encoding. In transformer, the authors propose a smart method which uses sine and cosine function to encode the position information. In Keras, we use the embedding approach, which embedded the positional information into an embedding vector. Then we add the input token vector with the embedded vector. We use embedding vectors for positional encoding because we want to handle the input sequence with different length. Okay, let's look at the positional embedding in Keras. First, we need to know the sequence length. So a downside of positional embedding is that the sequence length needs to be known in advance. And we need to know the length, so we know the input dimension. So this is the original word embeddings, the token, the input token. So there's embedding vectors, and now we have another embedding layer for positional encoding. The input is the sequence length, and we can define the output dimension need to be the same as the token embeddings, because finally we will add those two information together. And when the model is called, it will calculate both the embedded tokens and embedded positions. Okay, notice here, the both information are added together. So like the embedding layers, the information, this layer should be able to generate a mask, so we can ignore padding zeros in the inputs. The compute mask will be called automatically by the framework, and the mask will get propagated to the next layer. So we also need to compute the mask if necessary. Okay, so the key of positional encoding is to find a way to encode your position and then add the information with the original embedding vectors of the words. Now we are ready to combine the positional embedding with the transformer encoder. So first we pass the sequence length and the vocabulary size and embedding dimension to the positional embeddings, and we pass the inputs to the positional embedding first, and then we pass the output of the embedding, positional embedding to transformer. Okay, so now we add the positional embedding information into our transformer module. Other parts are the same as previous transformer encoder. Let's compare the classification accuracy of different models on the IMDB movie review dataset. We can see that the transformer encoder with positional encoding is slightly better than the original transformer encoder. So about 1% increase, 0.8% increase. The word embedding plus the mask bidirectional LSTM achieve 88% accuracy, which is good. The word embedding with bidirectional LSTM has 87, so masked bidirection is slightly better than the bidirectional LSTM. But the simple bigram and the unigram model can achieve very high accuracy. The bigram can achieve 90.4%. This is because the simple multi-hard vector can represent the review data very well, and also because we cannot handle very long sequence because of the memory, so we truncate the input review into 600, so it may reduce the accuracy slightly. Anyway, for this simple movie review classification data set, unigram and bigram, the bigram has achieved the best results. What is the rule of thumb to select the backup word or sequence model? The Keras author, Scholle, has conducted a large-scale research and find this rule. If the number of samples divided by the mean sample length is larger than 1,500, then you should choose the sequence model. If the ratio is less than 1,500, then you should select the backup bigrams. About IMDB movie review classification dataset, the value is less than 1,500, so we should choose the backup migrants. The result is intuitive. If you have enough training samples, long and a lot of training samples, then you should go sequence model. Otherwise, choose the backup migrants. This is the complete architecture of transformer with encoder and the decoder. Let's show the architecture again. So first, for the encoder, the transformer stack multiple encoders together, and each encoder has a multi-head attention with a residual connection and layer normalization. Then the feed-forward network, residual connection, layer normalization again. Then an encoded vector has been passed to the encoder-decoder attention, passed to another multi-head attention module in the decoder. Also, the decoder has been stacked there are multiple decoders. And also when training, we need to pass the output sequence or the correct answers into output to output self-attention, output self-attention, body head attention module, residual connection neural normalization, and the encoder decoder attention. So the output and the encoder, the decoder or the output self-attention has been, and the encoded input has been passed to the encoder decoder attention, and then again neural normalization, feed forward the network, dense projection, and finally neural normalization again, and this is the final output of the transformer decoder. So this is the complete architecture of transformer.